Hello, my name is Ali and I'll be going over the video assignment number 3 problem. So in this problem we have a toroidal inductor. It's made up of two ferromagnetic materials and it has two permeabilities, mu1 and mu2. And this is what it looks like. And as you can see, it's in a circular shape and it has a rectangular cross section. And these are the other variables that are used to define it. So this is the two parts of the question that we'll be doing. So in question 1, we have to derive an expression for the inductance. So if we look at the top view of the toroidal inductor and we imagine there's a current going down in it, right here, as we have, then using the right hand rule, we would know that the magnetic field in the inductor would be going in a clockwise direction. And this magnetic field would be identical for mu1 and mu2. The only difference is that the permeabilities are different, and that's shown right here. These magnetic fields are identical in the same direction. The only difference is their permeabilities. Now we can find the flux of each of these two regions, and that's done by using the surface integral of magnetic field. And right here we are extending the row from A to B because those are the two radiuses. So we're trying to capture all of the material. And then height wise, we're going from 0 to h over 2 because we're only looking at mu1 right now, and we're trying to find it for region 1. And so we solve this integral and we're left with this equation for the flux of region 1. And then now we can do region 2. It's the same process. One of the differences is that instead of z going from 0 to h, z is going from h over 2 to h because we're doing mu2, as you can see here, mu2, because we're trying to find it for region 2. So we do the same process and we're left with the same result, except mu2 is different. And now we can find inductance. In inductance, we multiply the number of loops by the flux and over the current. So the current gets cancelled out and the number of loops gets squared. And it's the same for the second material, only different permeability. And now we want to find the total inductance. And as we imagined earlier, a current going through the top, that would mean that the current is going through the top of mu2 and into mu1, and that could be kind of seen as the series configuration, and we know that we have to add series configurations. So that's what we do here with the inductances to find the inductance total. And now for question 2, we sub in these values into our equation over here, and we're left with 237 microhenries. This can also be looked at as 2.37 times 10 to the negative 4 henries. Now to find the stored magnetic energy in the inductor, we follow this. 1/2 multiplied by the inductance multiplied by current squared, and we know that current is 10 amps. So if we put 10 amps in this equation and everything, then we get 0.011 joules. But having all those zeros in front doesn't seem nice, so we can just translate that to 11.86 millijoules. And that is the total stored magnetic energy in the inductor.